June 11, 1943, Chance Vought Aircraft Factory, Stratford, Connecticut. In the metallurgical testing laboratory where aviation alloys were subjected to forces that would destroy lesser materials, Chief Engineer Charles Zimmerman stood before a propeller blade that should not have survived. The Hamilton Standard constant-speed propeller before him had endured a test protocol designed to identify failure points: extreme rotational stress, simulated bird strikes, temperature cycling from -60 to +200 degrees Fahrenheit, and finally deliberate collision with a steel barrier at combat-equivalent rotational velocity. The blade should have shattered. Instead, it bore a deep gouge across its leading edge but retained structural integrity that defied every prediction the engineering team had calculated. Zimmerman ran spectrographic analysis 3 times, convinced his equipment was malfunctioning. The results remained consistent. The alloy composition was wrong, not catastrophically wrong, but measurably deviant from the aluminum-copper specifications that had governed propeller manufacture since 1938. Someone in the supply chain had substituted a non-standard alloy, probably to meet delivery schedules during wartime material shortages. The substitution violated procurement regulations, quality control standards, and metallurgical best practices. It also produced a propeller that was virtually indestructible. Zimmerman marked the test report, "Urgent Command Review," and wondered if anyone would believe what the numbers revealed. The Vought F4U Corsair entered service in February 1943, with a reputation for brutal performance and equally brutal handling characteristics. Powered by the Pratt & Whitney R2800 double wasp engine generating 2,000 horsepower, the Corsair was the fastest fighter in American service, capable of 417 miles per hour in level flight. Its distinctive inverted gullwing design accommodated a 13-foot 4-inch diameter, Hamilton Standard hydromatic propeller, the largest propeller ever fitted to a single-engine fighter. That propeller was the critical interface between engine power and aerodynamic performance. It operated at rotational velocities exceeding 2,700 RPM under combat loads, generating tip speeds approaching supersonic velocity and subjecting the blade structure to centrifugal forces that tested the absolute limits of contemporary material science. The standard propeller specification called for an aluminum alloy designated 24S8, a copper-aluminum composition developed by Alcoa that offered excellent strength-to-weight ratios and predictable failure characteristics. When stressed beyond design limits, 24ST alloy would crack in controlled patterns that allowed pilots warning time before catastrophic failure. This predictability was considered a safety feature. Better to have a propeller that gave notice of impending failure than one that disintegrated without warning at combat power settings. But the Pacific Theater was revealing problems that laboratory testing had not anticipated. Corsair pilots operating from Henderson Field on Guadalcanal, from primitive airstrips carved into coral islands across the Solomons, and from the carrier decks of fast attack groups, were encountering operational conditions that exceeded every normal performance envelope. Propeller strikes against runway debris during takeoff, bird strikes at high-altitude cruise, fragments of shot-down enemy aircraft impacting propeller blades during close-quarters combat, salt air corrosion accelerated by tropical humidity, and constant exposure to seawater spray. The cumulative effect was a propeller failure rate that alarmed both operational commanders and safety inspectors. Through the first 4 months of 1943, the Marine Corps squadrons flying Corsairs in the South Pacific reported 17 propeller failures resulting in aircraft loss or serious damage. 3 pilots died when propeller disintegration led to engine failure over water. The standard 24ST alloy was performing exactly as designed. It was failing in predictable ways when stressed beyond specifications. The problem was that combat conditions routinely exceeded those specifications. The Corsair needed a propeller that could survive the impossible, not one that failed predictably when confronted with it. The material substitution occurred in April 1943 at the Hamilton Standard facility in East Hartford, Connecticut, where propeller production was running 24 hours daily to meet military procurement demands that seemed to increase weekly. Plant manager Donald Richardson faced an impossible logistics problem. His assembly lines required 12,000 pounds of 24ST aluminum alloy per day to maintain production schedules. His actual deliveries from Alcoa were averaging 8,500 pounds daily. The shortage threatened to halt Corsair propeller production at precisely the moment when Pacific commanders were screaming for more aircraft to contest Japanese air superiority. Richardson made a decision that violated every regulation in the procurement handbook. He authorized substitution of an alternative alloy designated 75S, a newer aluminum-zinc-magnesium-copper composition that Alcoa had developed for structural applications requiring higher strength than traditional aluminum alloys could provide. The 75S alloy was available in sufficient quantities because it was not yet approved for flight-critical applications. It existed in warehouse inventory precisely because cautious procurement officers refused to certify it for use in aircraft primary structures, until long-term testing validated its performance characteristics. Richardson was not ignorant of metallurgy. He knew that 75S had approximately 15% greater tensile strength than 24ST, superior resistance to crack propagation, and markedly different thermal expansion properties. These differences could be advantageous or catastrophic, depending on application-specific stress patterns. He also knew that if he did not deliver propellers, Marines would die for lack of air support. He authorized the substitution, marked the production logs with notation, alloy substitute, 75S, material shortage accommodation, and shipped 340 propeller assemblies to Chance Vaut for installation on Corsairs, destined for Marine Fighter Squadron VMF-124, then forming up for deployment to the Russell Islands. The propellers looked identical to standard units. They balanced correctly on testing equipment. They met dimensional specifications. The only difference was molecular structure invisible to inspection, detectable only through spectrographic analysis, that standard quality control procedures did not routinely perform. VMF-124 received their aircraft in May 1943, conducted workup training in California, and shipped to the South Pacific in June. Their Corsairs were equipped with propellers made from an alloy that had never been flight tested, never been certified for combat operations, and never been subjected to the engineering analysis that governed aviation safety. The substitution should have been a disaster. Instead, it became a revelation. First Lieutenant Robert Hansen, flying from Munda Airfield in the New Georgia Islands, recorded the initial combat encounter that revealed the substitute alloy's characteristics. August 18, 1943, escorting a strike against Japanese positions on Kolombangara Island. His flight encountered 8 Mitsubishi A6M0 fighters at 12,000 feet. During the engagement, Hansen executed a high-speed diving attack that pushed his Corsair past 450 miles per hour, well beyond the aircraft's tested velocity envelope. At that speed, any variation in propeller balance would have created vibrations catastrophic to engine mounts or airframe structure. His aircraft remained stable. More significantly, during a close-range firing pass, his propeller struck the tail section of a damaged Zero. The impact was severe enough that Hansen felt it through the control column, a shuddering collision that should have destroyed the propeller, or at minimum required blade replacement. Hansen completed the mission, returned to Munda, and reported the collision to his maintenance chief, Technical Sergeant Paul Morris. The expected finding would be stress fractures requiring propeller replacement. Morris inspected the blade and found a gouge 3 inches long and a 1/4 inch deep scored across the leading edge. But there were no stress fractures radiating from the impact point, no microscopic cracks visible under magnification. The blade had absorbed an impact that would have shattered a standard 24ST propeller and showed only superficial damage. Morris documented the inspection in his maintenance log with a note that would later prove historically significant. Blade damage from combat debris impact. No structural compromise detected. Blade remains serviceable. Alloy appears unusually resistant to impact fracture. He had no way of knowing the blade was manufactured from non-standard alloy. He simply observed that it had survived what should have destroyed it. Similar reports began accumulating from other Corsair squadrons equipped with the substitute alloy propellers. Propeller strikes that should have resulted in aircraft loss were instead resulting in continued operations. The anecdotal evidence was compelling enough that by September 1943, Marine Aircraft Group 12 requested engineering investigation into why certain batches of Corsair propellers seemed to demonstrate superior durability compared to others. The investigation led back to Hamilton Standard's production records, to Donald Richardson's unauthorized substitution, and ultimately to Charles Zimmerman's laboratory, where systematic testing would reveal that the wrong alloy was actually the right solution to a problem no one had properly defined. The systematic testing program initiated in September 1943 revealed material properties that challenged conventional understanding of aluminum alloy behavior under extreme stress. The 75S alloy demonstrated tensile strength 18% higher than 24T at room temperature, but more significantly, it maintained that strength advantage across the temperature ranges encountered in combat operations, from -40 degrees Fahrenheit at altitude to +180 degrees in tropical ground operations. The alloy's resistance to crack propagation proved even more remarkable. Standard metallurgical testing involves creating a controlled notch in the material and then subjecting it to cyclic loading until crack growth leads to failure. This reveals how the material behaves when damaged in service. The 24T alloy, when notched and cycled, would propagate cracks at predictable rates that allowed engineers to calculate safe service lives. The 75S alloy, when subjected to identical testing, showed crack propagation rates roughly 60% slower than 24T. More importantly, the cracks that did develop tended to arrest at grain boundaries rather than propagating continuously. The material was not merely stronger, it was tougher in the specific sense that materials scientists use the term, resistant to fracture even when flawed. Dr. Sarah Fieldstone, a metallurgist working at the Naval Research Laboratory in Washington, analyzed samples of both alloys under electron microscopy. Her findings revealed microstructural differences that explained the performance gap. The 75S alloy's zinc-magnesium additions created precipitation hardening effects that reinforced grain structure and provided barriers to crack propagation. The material was essentially self-reinforcing at the microscopic level. But the most unexpected property emerged during impact testing. When struck by high-velocity projectiles simulating combat debris, bird strikes, or propeller-to-propeller contact during formation flying, the 75S alloy demonstrated what engineers called graceful degradation. Instead of catastrophic shattering, the material would deform locally, absorbing impact energy through plastic deformation rather than brittle fracture. A 24T propeller struck at combat speeds would typically develop radial cracks from the impact point that would propagate during subsequent operation, eventually leading to blade separation. A 75S propeller struck under identical conditions would develop a localized dent or gouge but would not initiate the crack patterns that led to catastrophic failure. The implications were profound. The Corsair's propeller, operating at extreme rotational velocities and generating enormous power, was now made from a material that could sustain combat damage and continue functioning. The aircraft could absorb punishment that would have grounded earlier fighters and remain operationally effective. The institutional response to these findings revealed the tension between innovation and regulation that characterized wartime military procurement. By October 1943, the technical evidence supporting 75S alloy superiority was overwhelming. Yet the alloy remained uncertified for flight-critical applications. The Bureau of Aeronautics faced a paradox. Propellers made from unauthorized material were demonstrably superior to those made from approved specifications. Certifying the superior material would require admitting that procurement regulations had been violated and that aircraft had been deployed with non-compliant components. Captain James Thorne, the Bureau procurement officer responsible for propeller specifications, wrote in a confidential memo, "We have a material that performs better than specification in every measurable parameter. We also have a supply chain violation that should result in contract termination and possible criminal prosecution. Recommend immediate certification of 75S alloy for propeller applications and retroactive approval of all delivered units. Alternative is to ground aircraft equipped with superior components in favor of inferior, but compliant equipment, which serves no rational purpose." The memo reflected a pragmatism that became characteristic of American military procurement in World War II. Regulations existed to ensure safety and performance, but when battlefield results demonstrated that non-compliant solutions outperformed compliant ones, the rational response was to change the regulations rather than reject the improvement. By November 1943, 75S alloy was officially certified for propeller manufacture. Hamilton Standard's unauthorized substitution was retroactively approved. Donald Richardson received a commendation rather than a court-martial. The decision had immediate practical effects. Propeller production shifted entirely to 75S alloy by January 1944. The change required minimal retooling. The alloys had similar working properties and could be processed on existing equipment. but the performance implications rippled through the Corsair's operational capabilities in ways that extended far beyond propeller durability. With confidence that propeller failure was no longer a significant risk factor, pilots began pushing the aircraft harder. High-speed dives that had previously been limited by propeller stress concerns were now routine tactics. Low-altitude operations over rough terrain, where debris strikes were common, became operationally acceptable rather than unacceptably risky. The psychological impact on pilot confidence proved as significant as the material improvement itself. Knowing that a critical component could sustain combat damage and continue functioning changed how pilots approached combat, how commanders planned missions, and ultimately how the Corsair was employed as a weapons system. Major Gregory Boyington, commanding Marine Fighter Squadron VMF 214, the legendary Black Sheep, flew Corsairs equipped with 75S alloy propellers throughout his combat tour in late 1943 and early 1944. His after-action reports documented the tactical advantages that propeller durability provided in close-quarters combat. In one engagement on January 3, 1944, Boyington's propeller struck the wing of a Japanese fighter during a high-deflection gun pass. The impact was severe enough to cause momentary engine roughness as the propeller absorbed the collision. A standard 24ST propeller would likely have developed stress fractures, requiring immediate landing and inspection. Boyington's 75S propeller absorbed the impact. The engine smoothed out after several seconds, and he continued the engagement, ultimately downing 2 additional aircraft before returning to base. Post-flight inspection revealed the now familiar pattern: deep gouging but no structural compromise. The aircraft was returned to service within hours. This was not an isolated incident. VMF 214's maintenance logs from their 4-month combat deployment show 17 documented propeller strikes or impacts. 16 aircraft returned to service without propeller replacement. The one exception involved collision damage so severe that airframe structure was compromised. The propeller itself remained intact, even as the engine mount was destroyed. The operational tempo this enabled was unprecedented. Fighter squadrons could sustain aggressive tactics without the constant worry that propeller damage would remove aircraft from service. Maintenance officers could focus resources on genuine failures rather than precautionary replacements of components that might be damaged. The cumulative effect was increased aircraft availability rates that gave American units a sustainability advantage over Japanese forces whose logistical situation was deteriorating throughout 1944. But the durability that made the Corsair more effective also made it more dangerous to its opponents in ways that went beyond simple combat effectiveness. Damaged Japanese aircraft that collided with Corsair propellers in the chaotic proximity of dogfighting typically suffered catastrophic structural failure while the Corsair continued operating. The psychological impact on Japanese pilots was documented in captured diaries and post-war interviews. The American fighters seemed indestructible, able to collide with other aircraft and continue fighting as if nothing had occurred. This perception, while technically inaccurate, was grounded in the reality that 75S alloy propellers could sustain impacts that would have disabled earlier American fighters. The technical advantage translated into psychological dominance that influenced combat outcomes beyond the strict material capabilities of the aircraft. The industrial ramifications of the alloy substitution extended throughout the aluminum production complex that supported American aviation. By early 1944, Alcoa had shifted substantial production capacity towards 75S alloy manufacture, recognizing that military demand for the superior material would only increase as its combat advantages became widely recognized. But the production of 75S alloy was more complex than 24s to manufacture. The zinc and magnesium additions required precise temperature control during casting and heat treatment. The alloy's superior properties emerged from carefully controlled precipitation hardening processes that demanded metallurgical expertise beyond what standard aluminum production required. Alcoa invested heavily in process refinement, training metallurgists, and quality control systems that could consistently produce alloy meeting the tight specifications required for rotating components operating at extreme stress levels. The investment paid off in production efficiency that surprised even optimistic projections. By June 1944, 75S alloy production costs had dropped to within 8% of 24ST costs, despite the additional processing complexity. Volume manufacturing and process optimization had achieved economies of scale that made the superior alloy economically competitive with the standard material it replaced. This had implications far beyond Corsair propellers. The P-47 Thunderbolt, another high-power radial engine fighter, began receiving 75S propellers in spring 1944. The Navy's carrier aircraft, F-6F Hellcats, TBM Avengers, transitioned to the new alloy. By late 1944, virtually all American high-performance aircraft were equipped with propellers made from the alloy that had started as an unauthorized substitution to meet production schedules. The scale of the transformation was remarkable. In 18 months, American aviation had completely changed the material basis of one of its most critical components, not through deliberate research and development, but through a supply chain accident that revealed superior performance under combat conditions. This reflected a characteristic of American wartime industrial mobilization that often went unrecognized: the capacity to rapidly adapt and scale successful innovations, even when those innovations emerged from irregular channels. The 75S alloy transition required coordination across multiple industrial sectors: aluminum producers, propeller manufacturers, aircraft assemblers, maintenance depots, and training commands. The fact that this coordination occurred while industrial output was simultaneously increasing across all categories demonstrated organizational flexibility that matched the material flexibility of the alloy itself. Both the industrial system and the material it produced proved capable of absorbing stress, adapting to changing conditions, and maintaining performance even when subjected to demands that exceeded original design specifications. The unexpected durability of 75S alloy propellers created secondary tactical advantages that operational planners had not anticipated. Commander David McCampbell, Navy's leading fighter ace, recognized that the near indestructibility of Corsair propellers enabled aggressive tactics that would have been suicidal with less robust equipment. During the Battle of the Philippine Sea in June 1944, McCampbell led repeated strikes against Japanese carrier aircraft, often engaging at altitudes and speeds where propeller stress was extreme. His personal aircraft accumulated propeller damage from debris strikes, bird impacts, and one documented collision with a Japanese aircraft that disintegrated under his guns. None of these incidents required propeller replacement. His aircraft remained operationally ready throughout the four-day battle. This continuous availability proved crucial. The tactical advantage of having experienced pilots in serviceable aircraft throughout extended operations outweighed almost any other factor. McCampbell's 7 confirmed kills during the battle were made possible not just by his skill, but by his aircraft's ability to sustain damage that would have grounded earlier fighters. Marine squadrons operating from escort carriers documented similar experiences. The small carriers had limited maintenance facilities and minimal spare parts inventories. A propeller failure on a traditional carrier-based fighter would typically remove that aircraft from operations until replacement components arrived via supply ship, often a delay of weeks. Corsairs, equipped with 75S propellers, could sustain damage that would have destroyed 24ST propellers and continue operating with minimal maintenance intervention. Flight deck crews became accustomed to inspecting damaged propellers, finding stress patterns that should have mandated replacement, and instead simply documenting the damage and returning the aircraft to service when engineering analysis confirmed that the 75S alloy's crack-resistant properties meant the damage was superficial rather than structural. This operational flexibility was particularly valuable in the fast-paced carrier operations that characterized the Pacific War's final year. Task forces moved rapidly across vast oceanic distances, maintaining continuous combat operations without returning to major bases for extended maintenance periods. Aircraft had to remain serviceable under conditions that stressed every component to its limits. The 75S propeller's ability to absorb punishment without failing became a critical enabler of the operational tempo that allowed American carrier forces to dominate Pacific airspace throughout 1944 and 1945. The metallurgical accident that had started as a supply chain workaround had become a strategic advantage, enabling tactics and operational patterns that shaped the course of the naval air war. By late 1944, the combat data was conclusive enough to support quantitative analysis of the 75S alloy's operational impact. Marine Air Wing statisticians compiled maintenance records from 15 Corsair squadrons, 8 equipped with original 24ST propellers, 7 with 75S replacements. The data covered 6 months of combat operations across the Solomon Islands, Philippine Sea, and early Philippines campaigns. Aircraft equipped with 24ST propellers experienced propeller-related groundings at a rate of 3.7 incidents per 100 combat sorties. These groundings ranged from minor stress cracks requiring blade replacement to catastrophic failures that resulted in aircraft loss. The average propeller service life before replacement was 140 combat hours. Aircraft equipped with 75S propellers experienced propeller-related groundings at 0.4 incidents per 100 sorties, nearly a 10-fold reduction. Average service life extended to 380 combat hours, with several propellers exceeding 500 hours, before inspection revealed wear patterns that mandated replacement. The reliability improvement translated directly into operational availability. Squadrons with 75S propellers maintained average aircraft availability rates of 82%, compared to 68% for squadrons still operating 24ST equipment. Over a 6-month combat deployment, that difference meant approximately 40 additional sorties per squadron, 40 missions that could be flown because aircraft were not grounded for propeller maintenance. Colonel Clayton Jerome, analyzing the data for Marine Air Wing planning purposes, calculated the strategic implications. The improved availability was equivalent to deploying 15% more aircraft without actually increasing procurement, or alternatively, it allowed existing squadrons to sustain higher operational tempos without burning out equipment and crews. "We're not just talking about better propellers," he wrote in a December 1944 analysis. "We're talking about a force multiplier that emerges from material science. The same number of aircraft, the same number of pilots, achieving significantly greater combat effect because a critical component doesn't fail under stress." His analysis recommended accelerating 75S propeller deployment to all marine aviation units and urged the Bureau of Aeronautics to mandate the alloy for all future propeller procurement. The recommendations were implemented within weeks. The responsiveness reflected a military procurement system that had learned to recognize successful innovations and scale them rapidly. The bureaucracy that had initially resisted unauthorized material substitution now embraced that same substitution as standard practice once combat results validated the approach. The final validation of the 75S alloy's superiority came not from controlled testing or statistical analysis, but from the ultimate arbiter of military technology, survival in combat, where failure meant death. First Lieutenant Kenneth Walsh, already an ace with multiple confirmed kills, experienced the definitive test on August 30, 1945, 2 weeks after Japan's surrender, but while combat operations were still technically ongoing. Walsh was flying a patrol mission near Okinawa when his Corsair suffered engine failure at 8,000 feet over open ocean. The failure was unrelated to the propeller, a fuel system malfunction that killed the engine completely. Without power, Walsh faced immediate ditching, but the windmilling propeller, still rotating from airspeed as the aircraft descended, encountered extreme aerodynamic loads during Walsh's glide toward the water. A traditional propeller subjected to these loads while disconnected from engine power would typically experience blade pitch instability leading to structural failure. The blades would twist under aerodynamic pressure, exceed stress limits, and separate from the hub. Walsh's 75S alloy propeller remained intact throughout the powerless descent. The blades maintained structural integrity, despite experiencing loads and vibration patterns they were never designed to withstand. Walsh successfully ditched the aircraft, was recovered by rescue vessels within 20 minutes, and survived without serious injury. Post-recovery examination of the aircraft, raised from shallow water near shore, showed the propeller still attached and structurally sound despite having absorbed the impact, loads of water ditching while still rotating. The incident received minimal attention at the time. The war was over. Pilot survival stories were common. But to engineers familiar with propeller stress analysis, Walsh's survival represented something remarkable, a component that had exceeded every conceivable design specification and still functioned at the moment when functionality meant the difference between life and death. Dr. Sarah Fieldstone, the metallurgist who had analyzed the alloy's microstructure 2 years earlier, reviewed the recovered propeller. Her report concluded with an observation that transcended technical analysis. "We set out to build propellers that would survive combat damage. We succeeded in building propellers that can survive nearly anything. The margin between adequate and exceptional is often smaller than we imagine, sometimes just the substitution of one alloy for another. Her words captured the essential truth that the Corsair propeller story revealed. Excellence often emerges from unexpected places, and rigid adherence to specification can prevent the discovery of superior solutions. The post-war analysis of the 75S alloy's development and deployment revealed broader lessons about innovation, regulation, and the interaction between institutional constraints and individual initiative. The entire transformation, from unauthorized substitution to standard specification, had occurred in 26 months, a timeline that would have been impossible through normal peacetime procurement processes. Donald Richardson, the plant manager who had authorized the original substitution, was interviewed extensively by military historians documenting wartime industrial mobilization. His perspective provided insight into the human decisions that enabled material innovation. "I knew I was violating regulations," he testified. "I also knew that Marines were dying because we couldn't deliver propellers fast enough. When you're facing that choice, follow the rules and fail the mission, or break the rules and deliver what's needed, you make the decision and accept the consequences. I got lucky. The substitute alloy performed better than specification. If it had failed, I would have been court-martialed." The difference between innovation and recklessness is often just outcome. His honesty highlighted an uncomfortable truth about wartime innovation. Many successful developments emerged from decisions that violated established procedures, and their success was validated retroactively based on combat results rather than theoretical analysis. The institutional lesson was more nuanced. The military procurement system had demonstrated capacity to recognize and scale successful innovations, even when those innovations originated outside formal channels. But this flexibility emerged from wartime urgency. Whether peacetime institutions could maintain similar adaptability remained an open question. The 75S alloy itself continued in service long after the war ended. It became standard specification for propeller manufacture across military and civilian aviation. The material science breakthroughs that explained its superior performance influenced aluminum alloy development for decades, contributing to advances in aerospace, automotive, and structural engineering applications. By 1960, improved descendants of 75S alloy were being used in applications ranging from helicopter rotor blades to rocket motor casings. The metallurgical principles discovered through combat testing of Corsair propellers were enabling technologies that would carry humans to space. The lineage was direct and undeniable. A supply chain substitution made under wartime pressure in 1943 had contributed to material science knowledge that remained relevant into the space age, demonstrating that innovations born of necessity often have applications far beyond their original context. The final accounting of the F-4U Corsair's combat record reveals aircraft that achieved a kill ratio of 11.1 against Japanese opponents, among the highest of any American fighter in World War II. The Corsair flew more than 64,000 combat sorties, destroyed more than 2,100 Japanese aircraft in air combat, and provided close air support that proved decisive in campaigns from the Solomons to Okinawa. These statistics reflected pilot skill, tactical doctrine, and overall aircraft performance. But embedded within that performance was a component-level reliability that enabled the broader tactical success. Propeller-related failures accounted for less than 1% of Corsair operational losses after 75S alloy became standard, a rate so low it was statistically negligible compared to combat losses, pilot error, and other mechanical failures. The propeller had effectively been removed as a limiting factor in combat operations. This seemingly minor technical achievement had profound operational consequences. Pilots trusted their aircraft completely. Maintenance crews focused resources on genuine problems rather than precautionary component replacement. Squadron commanders planned aggressive tactics without factoring in propeller stress limitations that had constrained earlier fighters. The cumulative effect was a weapon system that performed at the edge of its capability envelope, without the reliability degradation that typically accompanies extreme operational use. The wrong alloy had become the right solution, not through deliberate engineering optimization, but through the convergence of wartime necessity, individual initiative, and willingness to validate innovations through operational results, rather than theoretical analysis. The transformation from unauthorized substitution to industry standard demonstrated institutional flexibility that matched the material flexibility of the alloy itself. Both the military procurement system and the aluminum alloy proved capable of adaptation under stress. Yet the story contained an element of randomness that resisted comfortable narratives about innovation and progress. If Donald Richardson had chosen a different substitute alloy, if the material properties of 75S had proven inadequate rather than superior, if combat testing had revealed failures rather than unexpected durability, the entire trajectory would have been reversed. The success was not inevitable. It emerged from contingent decisions made under pressure by individuals who could not fully predict the consequences of their choices. This uncertainty was characteristic of wartime innovation across all domains: radar development, nuclear weapons, code breaking, logistics systems, medical advances. The war created conditions where necessity overrode caution, where results justified methods, where retrospective analysis revealed that many critical breakthroughs emerged from paths that formal planning would never have authorized. The F-4U Corsair remained in production until 1952, with the final variants incorporating continuous refinements to the design that had proven so successful in World War II combat. The aircraft served in Korea, providing close air support with the same reliability that had characterized Pacific operations a decade earlier. Some Corsairs remained in military service into the 1960s, with smaller air forces, their 75S alloy propellers still functioning after 2 decades of operational use. The longevity validated what combat testing had revealed. The alloy possessed durability that far exceeded the airframe service life of the aircraft it equipped. Charles Zimmerman, the engineer who had first documented the substitute alloy's unexpected properties, spent the post-war years advancing materials science that built on lessons learned from the 75S experience. His work contributed to aluminum-lithium alloys used in modern aerospace applications, and to the development of metal matrix composites that represented the next evolution in high-performance structural materials. In a 1968 interview near the end of his career, he reflected on the Corsair propeller development. "We like to think engineering proceeds through careful analysis, controlled testing, and deliberate optimization. Sometimes it does, but just as often we stumble onto solutions through accident, necessity, or willingness to try approaches that theoretical analysis suggests are wrong. The 75S alloy was wrong by specification. It was right by every measure that actually mattered: performance, durability, reliability under conditions that exceeded our imagination when we wrote the specifications." His observation captured the essential paradox of the Corsair propeller story. The innovation that proved most successful was the one that violated established rules. The material that became industry standard was initially unauthorized. The component that made the Corsair nearly indestructible emerged not from deliberate research but from a plant manager's decision to substitute available material for specified material during a supply shortage. The lesson transcended materials science or aviation engineering. It spoke to the relationship between regulation and innovation, between formal procedure and practical necessity, between what theory predicts and what reality reveals. Sometimes the wrong solution is exactly right, not wrong at all, but simply beyond the boundaries of what existing frameworks can recognize as optimal. The challenge is building systems flexible enough to recognize these solutions when they emerge, and wise enough to validate them through performance rather than dismissing them for noncompliance. The Corsair's propeller taught that lesson in aluminum alloy and combat results. The lesson remains relevant wherever innovation confronts the constraints of specification, wherever improvement requires willingness to question what established wisdom defines as correct.